Hey, I would like to welcome Professor Rachel Oliver, and she will be giving us a webinar on the title of Nitrides for Quantum Light Sources. Professor Oliver received her Master of Engineering and PhD degrees from the University of Oxford, UK. She then moved to Cambridge as a research fellow at Peterhouse College and later won a prestigious Royal Society University Research Fellowship. In 2011, she took up her permanent academic position at the University of Cambridge, and she is currently Professor of Materials Science and the Director of the Cambridge Center for Gallium Nitride. She held a Leavenhulme Senior Research Fellowship in 2015 and 16, and delivered the Rank Prize Lecture in Photonics in 2018. She was one of the women in Engineering Society's top 50 women engineering in 2020. Her research focuses on understanding how the small-scale structure of nitride materials affects the performance and the properties of devices. Rachel is also a passionate advocate for increased equality, diversity, and inclusion in science and engineering, and a leader and a founder member of the Inclusion Group for Equity in Research in STEM, TIGERS. She's an equity and diversity champion for the University of Cambridge School of Physical Sciences, and has addressed the permanent parliamentary and the scientific community on equality issues. Okay, so Professor Oliver, please start.
Thank you very much. So hopefully everyone can hear me and see me all right and can see my slides. Hi, I'm Rachel.
Yes.
I'm speaking to you from Cambridge, where it is late and quite dark. I'm hoping it's more cheerful where you are. And the work I'm going to be talking about today, there have been many people, both in my group and my collaborators groups involved. My group is primarily a crystal growth group. We also do some device fabrication and lots of materials characterization using microscopes. And we work with both Robert Taylor's group at the University of Oxford and Professor Arakawa's group, the University of Tokyo, on the optical characterization of these materials, the quantum dot materials specifically. And we also have a theoretical partnership with the group of Stefan Schultz at the Tyndall National Institute, which is in Ireland. So yeah, without these people, this work would really never have happened, and I'm always grateful for all their efforts. Okay, so today I'm largely going to be talking about single photon sources. So what is a single photon source? Everyone's familiar with something like an incandescent bulb, the sort of light bulb you screw into the ceiling, and that's what we'd call a thermal source of light. And a laser is a coherent source of light, but they have something in common, which is that even if you block off most of the beam so that you are mostly getting no light at all out of that light source, you've still got a probability distribution of how many photons you'll see emitted. So even if most of the time you're getting no photons at all, sometimes you'll get one photon, but you still have a finite probability of getting a larger number of photons, like 3 photons or 5 photons, or I suppose even 17 photons. A single photon source is a light source that by its very nature emits exactly one and only one photon at a time. Preferably it does that with absolute fidelity and purity, and on demand you get exactly one photon where and when you want it. In fact, the devices aren't that good, but that is at least what we aspire to. So why would you want a single photon source? In some of my other research, I work on the sorts of light emitting diodes that are used in room lighting, that are solid state lighting devices for light bulbs. And there, a single photon is not very useful. It's not enough photons to light up my room, let me read my book, or find my way across the living room. So what are these devices good for? Well, they're enabling technologies for things like linear optical quantum computation and quantum cryptography. In linear optical quantum computation, the idea is we use standard or fairly sophisticated, but linear optical elements to guide and control photons, cause them to interact, and use that as a way to do quantum computation, massively parallel computation. Quantum cryptography is a way of securing information using the tenets of quantum physics. And in both cases, single photon sources would be really useful. Now, there are lots of different ways to make single photon sources, and I'm going to be focusing on single photon sources based on quantum dots. Specifically, I'm going to be talking about what I term epitaxial quantum dots, where we have a quantum dot, which is a narrow bandgap material grown as a small crystal on a substrate of a wider bandgap material and then capped so that our narrow bandgap material is completely surrounded by our wide bandgap material. And these are really tiny crystals on the few nanometer scale, and they have atom-like properties. We maybe recognize the hydrogen atom as having its S-like ground state for its one electron and a P-type, P-form first excited state with these two lobes. An indium arsenide quantum dot would have similarly a more symmetrical, but no, not here, spherical ground state for an electron, and then this two-lobed first excited state. The states of the electron in the quantum dot are somewhat analogous to the states of the electron in an atom. And just like with the hydrogen atom, if we want a photon out, we would have, for the hydrogen atom, an electron in the ground state, excite it to the excited state, it would fall back down and we'd emit one photon, but we couldn't have two at once because that would mean we'd need another excitation cycle to get the second photon. So we can look at the states available in a quantum dot, start with the quantum dot with no charges, for example, excite one electron to the ground state, falls back down, one photon out, and then we have to go through another excitation cycle to get a second photon. So a material that is atom-like in nature and hence by its very nature can act as a single photon emitter without having to attenuate the light source. But the thing about quantum dots, as opposed to single atoms, is that they can be incorporated into standard solid state optoelectronic devices, things for which we have an established processing technology. Okay, so something that's going to come up throughout this talk is going to be a test for single photon emission called the Hanbury-Brown and Twiss experiment. Okay. In this experiment, we have a beam of single photons, which are incident on a beam splitter. Now, if this were a laser beam, 50% of the laser beam would go to one detector and 50% would go to the other. But a photon can't go down both paths. It's a single fundamental pathway particle. It has to go one way or the other. And that means we should never have a photon, if we have a beam of single photons, arrive at this bottom detector and at the top detector simultaneously. When I kind of do demonstrations of this to maybe less expert groups than the one I'm talking to now, to general groups in the general public, I often talk about this in terms of like how I would prove that a tennis ball is a particle using a Hanbury-Brown and Twiss setup, or indeed a baseball, which is what I've got here. So this is something that I would normally show for, as I say, slightly less expert groups, but I thought might amuse you. So here my picture is my light source. They are going to produce my single photon, my baseball. And one of my catchers here is going to act as a beam splitter. And in the full version of the animation, I'm going to show you this is actually a simulation. So there's a 50-50 chance of the beam splitter transmitting the photon to one detector or an equally probability of them transmitting it to the other detector. So let's run this little animation. So the picture pitches the baseball, it comes to the beam splitter, and it's a coin toss decision, essentially, which detector it's going to go to. And obviously, the baseball never goes to both detectors. There's always a finite time interval between the baseball arriving at one detector and the baseball arriving at the other detector. Sometimes, because of the nature of random chance, several baseballs might just then go to the same detector. There's another one to the back detector. And then there'd be quite a long time interval between photons arriving, baseballs arriving at one detector and arriving at another. And sometimes it's a shorter interval, but there is always an interval. And if we measure the time interval between the photons arriving at one detector and the photons arriving at another, that can give us a signature of single photon emission, with us never seeing the case where we have photons arriving at both detectors simultaneously. So if I go back for a moment to my more scientific description of the Hanbury, Brown and Twiss experiment, here we've got what we call the correlation function. And this is basically measuring the probability of a photon arriving at one detector some specific time after a photon has arrived at the other detector. And that delay should never be zero, because we should never have a photon arrive at both detectors simultaneously. But we could have a photon arrive at one detector and then 20 nanoseconds later arrive at the other detector. Or we could have a photon arrive at one detector and then 20 nanoseconds earlier there have been a photon at the other detector. That would all be fine for a single photon stream. This is what we see for continuous excitation of our single photon emitter. But a lot of the experiments I'll show you today use pulse mode excitation. So essentially, we're like pressing the button and requesting a photon every 20 nanoseconds. And for the button press, buttons being pressed at these 20 nanosecond intervals, we shouldn't have a photon for a particular button press arriving at both detectors simultaneously. So again, we've got a missing pulse at time equals 0. But we could have a photon arriving for one pulse and then for the next pulse 20 nanoseconds later. Or we could have one arriving at the other detector 40 nanoseconds later, corresponding to a gap of 2 pulses. So here, the lack of a pulse at a delayed time of 0 is our signature of single photon emission. Okay, so you'll see traces a bit like that throughout this talk. But I'm going to be talking specifically about nitride semiconductors for single photon sources. And it's a perfectly reasonable question to ask why we're doing it that way. There's quite a lot of really excellent quantum dot single photon source work done in the arsenide materials, for example. So the arsenide materials are much better established than the nitrides. They have been used in optoelectronic devices for a long time. Why am I working with the more difficult and more recently developed nitrides? Well, one reason is that the nitrides allow us access to a huge range of wavelengths, from indium nitride in the infrared out to aluminium nitride in the ultraviolet. And where we might require different wavelengths of emission for different applications, the nitrides have the potential to enable that all across a single materials family. The other thing that's really exciting about the nitrides is that quantum dot single photon sources in this system continue to operate up to high temperatures. Mostly devices based on this kind of arsenide phosphide type material system only work at a few Kelvin to a few tens of Kelvin. This is from Mark Holmes' group. This is not my work, but it's a really lovely example of what the nitrides can achieve. And here we have a single photon emitter, which is operating at 77 degrees C. Note 77 Celsius, above 0, not 77 Kelvin. This is a temperature which would be hot enough to cook an egg. So this is really exciting in terms of potential real world applications and not having to use liquid cryogens to do this type of experiment and this type of technology. Okay, so some of you may know a ton about the nitrides. If you don't, here's just a little bit of a primer. These are, as I say, materials that have band gaps spanning the visible spectrum and out into the ultraviolet and the infrared. For our kind of light bulb technology, which is the classic nitride technology, we're usually talking about blue emitting devices. And that's absolutely the most common thing for the nitrides, is making devices emitting blue light. They are then, for your light bulb, some of that blue light will be converted into white light using a phosphor material. A material like gallium arsenide, you'd be able to buy as a large single crystal or a large single crystalline wafer. That's difficult still in the nitrides. There are increasing amounts of bulk material available, but it's very expensive and hard to come by. So we grow almost all our commercial devices heteroepitaxially on unlike substrates, most commonly silicon, sapphire, or silicon carbide. That means that because of the difference in lattice parameter between the substrate and the device grown on top, you tend to get a lot of defects in these materials. These defects are dislocations, line defects, which run straight through your whole nitride film, sort of threading through your device. We call them threading dislocations. Another thing that's different between gallium nitride and gallium arsenide is that gallium arsenide is a cubic material and gallium nitride is hexagonal. This is the hexagonal crystal structure here. One peculiarity of that hexagonal crystal structure is that it's polar. there is a uniqueness to what I've got labeled here as the 0001 axis. It isn't related by symmetry to the 0001 axis in the opposite direction. That polarization and also the fact the material is highly piezoelectric means that when we grow strange structures, like here, a indium gallium nitride quantum well, where the indium gallium nitride will be in compression, internal fields arise from the polarization, strain related and spontaneous within the crystal structure. And those internal fields tend to separate electron and holes, driving them to opposite sides of here, a quantum well, but could equally be a quantum dot. Now, if I'd given this talk 10 years ago, I would probably still have been mostly talking about one device, the first indium gallium nitride single photon emitter that I made, which was made on the polar C plane of gallium nitride. The crystal structure I showed before, I've kind of taken the atoms out of here, and I'm just showing the crystal structure as essentially a hexagonal prism. The C plane is the top face of that hexagonal prism, highlighted in green. We can look at a number of other common planes, such as the M plane, which is a side face, the A plane, which is at some angle to that side face, but still perpendicular to the C plane. And there are also semipolar planes at kind of jaunty angles in between. The C plane is the most commonly grown way to orient a nitride film. It's the way that almost all LED materials are made, for example. And it's also the direction, although we're very good at growing it, that is most susceptible to those internal electric fields. This is the direction along which the polarization of the crystal naturally points. Okay, so that was where we started with this common polar C-plane material. And we made the first indium gallium nitride single photon source in my lab in Cambridge. You can see here a black trace, which is our Hanbury, Brown and Twist trace for that first device. It's quite noisy. The device was not as bright as we might have liked, and our experiment wasn't as sensitive as we might have liked. But we can see that we've got these pulses and then a nice clear dip at time equals 0. The red dashed line is the laser that we use to excite this device. It's an optically pumped device at this stage. And you can see that doesn't have this nice deep dip at time equals 0, because the laser isn't a single photon emitter. And we've got the signature that we were looking for, proving that these indium gallium nitride quantum dots act as single photon sources. Now, as I say, at the time, I could have given you a long talk about all the materials difficulties of getting to that device. What I have mostly spent the years since I made that device doing is finding out things that are wrong with it. So now I'm going to tell you a lot about what was wrong with my early devices. Really, the big problem is this internal electric field along this C-axis, which along the length of my hexagonal prism, it separates the electron from the hole in these quantum dots. This is a simulation from Stefan Schultz's group of one of our quantum dots. And the consequence of that is because the electron and hole are pulled apart, their wave functions, electron wave function in red and hole wave function in green, don't actually overlap all that well. And that means that they take a long time for the electron and hole to recombine with one another. And we get long emission lifetimes. Now that just limits how many single photons you can have per unit time. It limits the transmission rate of data on your single photon source. It also has other consequences. We already have said that we have these internal electric fields. And here I'm kind of modeling my quantum dot for simplicity, just as if it were a quantum well. So these internal electric fields separate the electron and the hole. We also have a whole lot of defects in these materials, these dislocations due to heteroepitaxial growth. They create states in the band gap and charges get trapped at them. So there's a field associated with those charges. And that means we kind of sum up the field associated with the charge and the internal field in the quantum well. And that gives a slightly different overall field in the quantum well, which gives a different wavelength of emission and a different intensity of emission. So if we can have many different traps around my quantum dot, and so they're sometimes charged and sometimes uncharged, and the charges hop on and off them, then instantaneously we might have a quantum dot emission like this, just as a sketch, and then a few nanoseconds later, perhaps, we'll have a different wavelength for the emission and then another different wavelength for the emission as the charge environment changes and fluctuates. All these different wavelengths will then kind of sum up to the emission we see, which will be a much wider peak than we might ideally expect from a quantum dot. So we see this charge trapping phenomenon in wide line widths in the quantum dot emission. Sometimes actually the charge trapping phenomenon is happening on a much longer time scale, and we can actually just measure it happening, watch the line from the quantum dot wandering about in wavelength space. So this graph here has time up the y-axis, and the wavelength of emission on the x-axis, and the intensity of the emission is plotted as the color, with the bright emission being the red part. And we can see that this red band changes by, a few tenths of a nanometer every few seconds, basically hopping from one state to another as a particular adjacent charge or adjacent state charges and discharges. Now, that's not great. For some applications, you might want your photons to be indistinguishable, and clearly they're not. They're all coming out at different colors. That is not indistinguishable photons. You might want to build a device where your quantum emitter is on resonance with the cavity. Your cavity will be designed for a particular wavelength, but if your quantum dot keeps changing the wavelength which it emits, it won't necessarily match the cavity at any given moment. This spectral wandering is really going to be a nuisance to us in any potential applications of this device. So how might we get rid of the spectral wandering? Well, the internal electric fields tend to be along this c-axis, up the axis of the long axis of my hexagon. If we go at 90 degrees to that, in a quantum world, we'd actually completely eliminate the internal fields. For a quantum dot, we've still got a in-plane c-axis, which is left to right in my diagram here. And that means we will still have a like interfaces which are at least at some acute angle to that c-axis, and we'll still see some in-plane separation of the electron and hole. But we should theoretically be able to bring the electron and hole much, much closer together in this case. Bringing the electron and hole together should reduce the emission lifetime, and it should also reduce the spectral diffusion. So one of the first questions I'm going to ask in this talk about growing quantum dots on this non-polar crystal face is this true? Can we demonstrate these advantageous properties? I've got other questions to ask though, because we're really good in the nitride community at C-plane growth, but other crystal orientations like the A-plane that I'm showing here, we're a lot less good at that. So with this immature growth and processing technology, we've got to deal with the fact that we're doing heteroepitaxial growth in a new orientation, and we've got a load of defects, not just the dislocations I showed before, but also another family of defects, planar defects called stacking faults. So given that this is a immature growth technology, can we make any useful devices at all? And those are the two questions I'm going to answer in the rest of this talk. Okay, so I've shown you my first C-plane device. We're now going to move on to how we made quantum dot single photon sources based on A-plane indium gallium nitride on this purple plane I've had illustrated for the last few moments. The quantum dot growth method we use in Cambridge is a little unusual. We don't use a sort of classic Stransky-Krasnov growth mode. We don't find it works all that well. Instead, we use something called modified droplet epitaxy. Droplet epitaxy is where you deposit metal on the surface and let it ball up into droplets. And then you react it with your group 5 species, typically say arsenic and gallium arsenide, to form crystalline regions which will become quantum dots. In our technique, we start off with an indium gallium nitride thin layer. We anneal it to form indium-rich regions, and they decompose, leaving indium and indeed actually gallium on the surface. That then balls up into these tiny metallic droplets, and then we reintroduce ammonia and produce our indium gallium nitride crystals. As some interdiffusion goes on, the structures are somewhat chaotic. Nonetheless, it gives really, really bright quantum dot emission. Pragmatically, it works really well. So this is the sort of structure we grow on the C-plane. This is prior to the nitridation step. So this is actually the metallic droplets we are looking at here. And we can see that what we have is this kind of distribution of these tiny metallic droplets and also an indium gallium nitride film with holes in it. So we have a sort of quantum well layer with holes in, and on top of that, these little metallic nanostructures, which we're going to react with nitrogen to give our quantum dots. If we carry out the same process under actually really similar conditions on the A-plane, the morphology isn't the same, but it has some broad scale similarities. We've still got our little tiny metallic droplets. Here are the sparse, but that's not a bad thing when you're making single photon sources. It allows you to separate out individual dots. And we've got a quantum well layer that in this case is rather more decomposed into nanoscale areas, but is still, a quantum well layer with holes in. And those quantum dots, once we kind of complete the droplet epitaxy process, show kind of typical spectral features of quantum dot emission. We have these very sharp peaks. So this atom-like nature, this gives us a delta function-like density of states in the quantum dot. And that means that the emission from a single quantum dot, a single state and a single quantum dot is really kind of a spike, very sharp. However, if we look at the lifetime of that emission, it's now a great deal shorter. And that's the signature we were looking for of the reduction in the internal fields. The lifetimes here are about an order of magnitude faster than I was showing for similar wavelength emitting quantum dots on the polar sea plane where the electric fields tend to dominate. So that's kind of what we were expecting. That was the thing we were aiming to do by growing these non-polar quantum dots. So yay, we're there, great. But we also discovered that there are other things that are quite interesting and quite nice about these A-plane quantum dots. They are more stable to temperature than the C-plane quantum dots. Here I'm looking at how the line width of the quantum dot broadens against temperature. And the A-plane dots remain very narrow, even up to about 140 to 150 Kelvin, when the C-plane dots are significantly broadened. Also, the light from these A-plane quantum dots tends to be linearly polarized. We've got the emission here at two orthogonal directions in terms of the polarization. You can see that for this emission here, at about 485 nanometers, we've got nothing at all in the 90-degree orientation and a very, very strong emission in the 0-degree orientation. It's just worth mentioning that we don't necessarily do all our quantum dot growth on the A-plane using this droplet epitaxy approach. We do also grow dots in a slightly more traditional strain-driven method. It's a bit like SK growth, but not quite. There are some kind of distinctive weird issues with it that make it dissimilar. But these quantum dots nonetheless are grown in a more traditional method, and they show actually very similar properties to the droplet epitaxy dots. Very short lifetimes, down to 150 picoseconds in this case, good temperature stability. Here we're showing a quantum dot which is losing intensity at 200 Kelvin, but still clearly detectable in emission. And this highly polarized emission that we saw again in the modified droplet epitaxy. Now, the sort of simplest devices we make with these dots are still going to be optically pumped devices. I'll come on to electrical pumping later. And we just etch little pillars to help isolate individual dots and also to guide the light and improve light extraction. These were done in a really simple fabrication route. We disperse 200 nanometer silica spheres in a very sparse array across the surface and use them as a mask then to etch the pillars. So it's a microsphere or nanosphere lithography technique. From a dot here in the pillar, we can see very nice sharp emission at low temperature, broadening above about 140, 150 Kelvin, but we still have detectable emission up at 250 Kelvin. So compared to a typical arsenide quantum dot, really quite good temperature stability. Not as good as Mark Holmes and his ability to cook an egg, though, I have to admit. And do these dots generate single photons? Well, yeah, they do. So this is the data recorded at 4 Kelvin. And we can see this dip in the Hamby-Brown and twist trace. And the same, the data recorded at 220 Kelvin, a much higher temperature. And again, we have a dip. Now, two things to note about this data. I said we would like there to be a dip down to 0, and we've got a dip down to about 37% of the average of the surrounding peaks. That's a fact about these devices. It's not good, okay? We want really pure single photon emission. In general, in the community, your dip kind of is respectable to say you've got a single photon emitter as long as it's less than 50% of the surrounding peaks, which is why we are claiming we have a single photon emitter up to 220 Kelvin. We still have a dip at 250 Kelvin. It's just not below 0.5 in terms of the comparison between the surrounding peaks and the central peak. So yeah, okay, it's a single photon emitter, fine. But in applications, these extra photons, which are contaminating the single photon stream, are a problem. they are probably from that fragmented quantum well layer that I showed you when I explained how the growth works, other regions of material not in the quantum dot, but emitting at the same wavelength. Quite often when people do this type of analysis, they use a subtraction technique to remove that background, say, oh, look, we have beautiful single photon emission from our quantum dot. I generally try not to do that because, yeah, okay, the quantum dot may be a single photon emitter, but if you can't make a device where you eliminate the other photons from other sources, then the fact that you can use a kind of mathematical trick to get rid of those excess counts in your trace is not really all that interesting. So yeah, I'm very pleased with this device, was when I grew it anyway, that it operates up to these fairly high temperatures accessible by Peltier cooling, which might be quite useful in practical applications, but it does have an issue with this background emission. I showed before that these dots emitted linearly polarized light. This data now on the polarization is from the same dot where I showed the Hamby, Brown and Twist data. And again, we have highly polarized light. The degree of polarization here is 83%. And we can also use some of the structures that we grew to help reduce defects in these materials to understand the alignment of the polarization relative to the alignment of the crystal structure. So the polarization axis here is along the in-plane 1 bar 100 direction, and that's common across the vast majority of the dots that we see. So it's not just that the emission is polarized, it's deterministically polarized. We know that all the dots are going to have light polarized in the same direction. We have control over the polarization state. Just showing you some statistics of that on this next slide. We can see that the average degree of polarization amongst these dots is about 90%, but within our ability to measure, some of the dots are 100% linearly polarized. Why do we get this high degree of polarization? Well, it's to do with the strain in the quantum dot and the nature of the crystal plane. So the C plane, where we normally grow, has an symmetric strain state. You only really have to worry about the difference between the A parameter of the film and the A parameter of the substrate, and it's symmetrically strained. And in that case, you can see that we have this overlap between different hole bands. Okay. However, for the non-polar planes, we have asymmetric strain, and that asymmetric strain lifts the degeneracy of the upper two hole bands. This is well known in quantum wells and gives polarized emission from quantum wells in this these non-polar systems. And the same applies to the quantum dots. This lifting of the degeneracy results in the polarization emission that we see. So when I started talking about these non-polar dots, I said that what I wanted was to get faster lifetimes, which we've shown, and I wanted to get less spectral diffusion. So now we're going to look a little bit at the spectral diffusion from these quantum dots, starting off looking at it on the long time scale. So looking over a period of tens of seconds, how the wavelength varies. I've got both my sort of strain-driven dot growth here in blue and the droplet epitaxy dots in red. In both cases, you can see that compared to the trace I showed earlier, we aren't seeing very many of these huge jumps we were seeing before. So it looks quite a lot better. Trying to quantify that a bit, we can measure the variation of the energy and how much excursion from the average energy we see and how frequently that occurs. And what we're measuring here is like the average size of the jumps that we see for the strain-driven and the droplet epitaxy dots. And that's giving us kind of nice low values, particularly for the strain-driven dots. Now, what I haven't got on here is anything for the C-plane dots. Are we really seeing an improvement? So I'm just kind of taking the average here as a blue line for the strain-driven dots and a red line for the droplet epitaxy dots on the A plane. Bringing in C plane dots, they are slightly worse on average than the modified droplet epitaxy dots, but maybe this isn't the sort of vast change I was hoping to see. The trouble is we're not really making a fair comparison here because our droplet epitaxy dots, because of this immaturity of the A-plane system, contain a lot more defects than the low defect density C-plane material we commonly worked on when we mostly focused on the C-plane. If I want to look at an equivalent defect density on the C-plane, I actually have to kind of make my graph a bit longer, because my high defect density C-plane material, which has a very similar density of these crystal faults to my A-plane material, has a much, much higher extent of spectral diffusion. So we think we really are achieving improvements by moving to the A-plane in this spectral diffusion issue. The data I've been showing so far has all been about the long timescale spectral diffusion. But I said that the line width of a nitride dot is often made up of multiple different emissions at slightly different wavelengths, all superimposed on one another. And that change between the different wavelengths can be on a very short timescale, picosecond or nanosecond type timescales. How will we measure that? Well, Salon et al. In Nature Photonics came up with a nice way of doing this. Instead of doing their Hanbury, Brown and Twist experiment on the whole peak, they divided the peak into two halves, like a low side, low energy side, and a high energy side. And we can imagine that the emission on the low energy side is about half the single photons, and the emission on the high energy side is the other half. And we get several emissions on the low energy side, and then a charging or decharging event occurs in the environment, and we switch to the high energy side, get a few emissions, and back to the low energy side. If we do our Hanbury, Brown and Twist experiment on just one side of the peak, we just see one of those sets of bunches of photons. So we get a bunch of photons emitted on the low energy side, and then nothing at all if we're only monitoring the low energy side of the peak. And if we do, therefore, a half line width autocorrelation experiment, we pick up that bunching, that tendency of the photons to arrive in bunches, as a rise in our correlation function. And the time scale of that drop-off gives us an idea of the time scale on which we're stable on one side or the other, the low energy or the high energy side. So using this approach, we can work out an estimate of how fast this fast timescale diffusion occurs. Applying that in the non-polar A-plane quantum dots then, I've just got two quantum dots here from really quite a large number that we have measured. And you can see these spectral diffusion timescales vary quite a lot. The shortest one we've measured is about 70 nanoseconds, and the longest is about a microsecond. Now, I think the level of variation here is down to just how defecty this material is, and the defect density is quite homogeneous. So some quantum dots are much less influenced by defects than others, and that's still something we're thinking about and learning about. What's quite exciting, though, is just how long our longest spectral diffusion timescales are, because if we can optimize our growth to make that the norm in these samples, that's a really pretty impressive number. For comparison, the longest timescale of spectral diffusion from cross-correlation measurements seen on polar C-plane indium gallium nitride dots is about 260 nanoseconds. And these numbers of a few hundred nanoseconds are actually sort of quite similar to what's seen in the arsenides. Now, the reason we care about this is we want the quantum dot to stay at the same wavelength to give us some chance of having indistinguishable photons. If it wanders about, our photons ain't going to be indistinguishable. Now, in the arsenides, we maintain that indistinguishability for a few hundreds of nanoseconds. In the nitrides, we kind of assumed that spectral diffusion was going to make it impossible for any useful number of repeats to be given with indistinguishable photons. But actually, this is telling us that by using these quantum dots that are less influenced by the internal electric field, we can get away from that problem. And it is potentially possible that we could get indistinguishable photons in these nitride dots. Okay, so I hope I've shown you that the potential advantages of working on this non-polar A-plane that I mentioned are really showing up. We are seeing shorter emission lifetimes. We are seeing reduced spectral diffusion. Those were the things we were kind of expecting to see. As a bonus, we've also got improved temperature stability and highly polarized emission. So we're pretty excited about these dots. But can we make them into real devices? Okay, so the only thing kind of resembling a device I've shown you so far are these little pillars, which are optically pumped. If we look at what people are achieving in the arsenide material system, this from the group of Stefan Reichenstein, then they have some really quite sophisticated devices in comparison. Their dots are in cavities sandwiched between top and bottom distributed Bragg reflectors. They get coupling between the dot and the cavity. They get lots of, therefore, photons emitted from the device. And then they can actually contact to these cavities using these ring type electrodes and electrically pump their devices. So this is a cavity and it's a single photon emitting diode structure, electrically pumped. I'm saying right now, we aren't there yet. What I'm going to show you is the steps we have taken in that direction with the rather more challenging nitride materials. So this is our first single photon LED in the non-polar. We've done this previously in the polar C plane. We're using our strain-driven quantum dots here. That's just what happened to work. I can't really tell you why. Quite a simple LED structure with a PIN structure. A little bit of extra care has to be taken in the processing to make the contacts, to make the device survivable for the low temperatures. But we have diodes, and although we increase the turn-on voltage, we see that they do operate as diodes at even down to 4.5 Kelvin. This is my first single photon electroluminescence trace from such a device. Now, you're going to look at that and say, that is not a very good dip, Rachel. You said you were looking for dips down below 50% from the background level, and we haven't got that. This is a continuous wave device rather than the pulse mode I was showing you earlier. Now, the trouble with this device is that our non-polar dots with these very short lifetimes are starting to make our lives very difficult in the lab. I'm zooming in now around the dip. And what we can add into this diagram is the instrument response function of the detector we're using to measure this dip. And you can see that it's actually got almost the same width as the dip we're seeing. So this data is hugely affected by the inability of our detector to really keep up with these very fast emitting quantum dots. If we deconvolve the impact of the detector from our data, we actually see that we'd estimate the dip to be down to about 0.4. And we can also use the same data, same fit, to estimate the lifetime of the dots here as being about 100 picoseconds. So by nitride standards, really very speedy emitters. Now, what I'm not doing here is subtracting a background. The background counts are still here. So the thing that I said, oh, people shouldn't be doing because it obscured the problems with the device, that problem's still in my data set. What I'm doing is taking out the fact that the detectors we had in the lab when this experiment was done were not really equal to keeping up with the fast emission of the device. So we do have a single photon emitting diode, a step towards the more sophisticated device that I showed you. The other thing that's in this device that I'm kind of targeting based on what's been achieved in the arsenides are these distributed Bragg reflectors. For anyone who's not familiar, I'm sure most of you are, a distributed Bragg reflector is essentially a multi-layer mirror. We have alternating layers of high and low refractive index. We have reflection of light at the interfaces between those high and low refractive index layers, where we have the correct relationship between the wavelength of the light and the spacing. We will then see constructive interference. So for that wavelength, we'll get very strong reflection, whereas for other wavelengths, we'll see very little reflection due to destructive interference. So it's a wavelength specific semiconductor mirror. If you want to make one of those in the arsenides, you use gallium arsenide and aluminium arsenide because they have the same lattice parameter, almost, okay? A lattice match material pair, okay? That's great, and that allows you to make great big stacks in your DBR that are unstrained and that therefore the material's growth does not deteriorate. Unfortunately, we're working in gallium nitride. So if we're talking gallium arsenide, aluminium arsenide, the equivalent would be gallium nitride, aluminium nitride, and they don't have the same lattice parameter. And that causes a lot of problems with the growth. So this is that kind of region of the diagram, which is band gap versus lattice parameter, but zoomed in a bit. Can't lattice match gallium nitride and aluminium nitride. They definitely have different lattice parameters, but we can lattice match gallium nitride to aluminium indium nitride at 18% indium. And we can see what the impact is here of that lattice matching. This is a gallium nitride, aluminium nitride DBR. The aluminium nitride is in tension on the gallium nitride, it tends to crack. That causes imperfections and changes in the thickness of the layers, which reduces the reflectivity. Also, the strain leads to a plethora of extra defects. The aluminium indium nitride, though, which is lattice matched, we have rather beautiful, perfect layers over a really, really large stack. And that's great. But the lattice parameter I'm looking at here is the A lattice parameter. If I'm looking at C plane, the A lattice parameter is all I have to worry about. If I'm looking at A plane, I also need to worry about essentially the height of my hexagonal prism, what I'm indicating as a C lattice parameter here. So now we need to look at the C lattice parameter and the same thing, lattice parameter versus band gap, and you can match gallium nitride to aluminium indium nitride in terms of the lattice parameter at 28% indium, which is fine, except here I need to match both A and C. And I can't grow aluminium indium nitride, which simultaneously has 18% and 28% indium. This is not an option on the A plane, this approach of lattice matching. There is no lattice match pair. So we had to find a different lattice match material. The other problem with aluminium indium nitride, gallium nitride, is that there's not much refractive index contrast between those two materials. So you need a huge numbers of layers to get a high reflectivity. Also, the growth of aluminium indium nitride is really slow to get high quality material. The thing we swapped to was working with porous gallium nitride. Here we're using an electrochemical etching of doped gallium nitride to create porosity in the material. And the pores, basically adding air as a kind of gallium nitride air composite, lower the refractive index. Doped GaN and GaN have hardly any lattice mismatch, so we can get rid of all these strain effects we were worrying about in aluminium nitride, gallium nitride. And because the refractive index decreases with the porosity increase, if we've got a high porosity, we can get a very high refractive index contrast. Also, it's really fast to grow, but we do then have to add an etching step to form the porous gallium nitride. This is the kind of etching we're doing. It's electrochemical etching in oxalic acid, typically, which is a fairly benign acid. We're using the sample as the anode, and we have a platinum foil cathode, and we apply a positive bias. Whole injection into the NGAN then drives local oxidation. The gallium oxide thus formed, dissolves in our acid electrolyte, and we etch pores. We can vary the pore size by changing the conductivity or by changing the doping density. We can also see changes in pore size related to changes in bias. Now, this is a sample where I have different doping densities in different layers, and you can see the high dope material at the top has a much higher porosity than the lower dope material further down. These porous layers are separated by undoped layers, which tend not to etch. And you might look at this and think, okay, they've made a gallium nitride sample, they've cracked it open and provided an exposed surface for the etchant to access the pores. We etched the sample and then cracked it open so we could see the pores. The etching here is coming through the undoped layer, which appears intact and unetched. I'll explain how that happens in a second. So we're doing this for DBRs, which means we need a alternating high and low refractive index structure, which starts off as an alternating highly doped, undoped structure. We apply our electrochemical technique and we make something like this. This is an A-plane distributed Bragg reflector with layers of doped and of porous and non-porous material. What I want to stress here is that we do this here on a little chip, but at up to the full wafer scale with no other processing steps except for the electrochemical etch. The concept of porous GaN was very much introduced to the nitride community by Zhang at Yale. And what they do is they start off with this very similar epitaxial structure. They cover the surface in silicon dioxide. They open windows with lithography in the silicon dioxide. They reactive ion etch through to expose sidewalls, and then they electrochemically etch to form their porous DBR. Now that's quite a lengthy process, it adds quite a lot of complexity, and it can place limitations on the next part of the device fabrication. We don't do any of that extra lithographic steps. We work with the entire wafer. And the etchant is axing dope layers via defect channels that go through the undoped layer. Key thing is that after we've formed the porous DBR, we've still got a fairly smooth surface. A-plane surfaces are not as beautifully smooth as we get on C-plane anyway, but we have a very similar RMS roughness, not much change to the surface morphology at all. And we can see there's a lot of defects in this TEM imaging cross-section, but we're not seeming to do much to the defect density either. We're not making the material, it's not great material, but we're not making it any worse. And by changing the layer thicknesses in our porous structures, we can tune the wavelength of the reflectance, get very nice high reflectances from usually sort of 10 layer, 8 layer structures because of this large refractive index contrast, but at any wavelength we happen to design for. The material here is also conducting, although not as conducting as before, porosified it. I'm just going to unpack that porosification mechanism that I've mentioned, that we're etching through defect channels. What I've got here is a cavity structure with a porous DBR above and below a quantum dot layer in the center. But what I want to focus on is that we did a transmission electron microscopy experiment where we took out just one layer of the porous DBR. Okay, we've prepared this as a very thin foil that will be electron transparent in the transmission electron microscope. This is a scanning transmission electron microscope image, STEM, okay? And STEM is generally thought of as a technique which gives you atomic mass contrast. Heavier elements is brighter. Here we've only basically got gallium nitride. So it's really just giving us thickness contrast. Where there's more material, we're seeing brighter. When there's less material, we're seeing darker. And what we see in this porous layer are these little black holes, okay? And then emanating from those holes, the mid-gray is the pores, with the white being the walls between the pores. And we can see that the pores emanate out from these little dark holes, and where pores emanating out from different holes bump into one another, then we have a kind of wall between the two domains. If we then zoom in on one of these little black holes, this is now an atomically resolved STEM image of such a hole. What we've done is drawn what's called a Burgers circuit around that hole. Now, a Burgers circuit is a circuit that if you draw it in a perfect crystal, it closes. So we take here sort of a fixed number of steps in each of our 6 symmetry-related directions, and we should come back round to the starting point in a perfect crystal. But going around this hole, we don't close that circuit. There's an error in closing the circuit of essentially 1 lattice spacing. That's what we call the Burgers vector. And that shows that what there was at the center of this hole is a dislocation core. The dislocation is basically still there because the displacement still exists. But the distorted region of bonding at the very, very heart of the dislocation has been etched away, leaving behind a pipe down which our etchant flows. And that's how we can etch through these undoped layers to access the doped layers below and create these multi-layer distributed Bragg reflector structures. Okay, so summing up a little bit, I have shown you these potential advantages of using non-polar quantum dots, so shorter emission lifetimes, reduced spectral diffusion, improved temperature stability, and highly polarized emission. And I've also shown you we can make some steps towards some interesting devices. We've made single photon LEDs and we've made distributed Bragg reflectors. So where do we go from there? We're obviously making progress, but we haven't kind of finished this story at all as yet. Well, I want to show you our first porous gallium nitride quantum device. This is a polar gallium nitride device grown on the C plane, where we still do work, although we've had a lot of emphasis on the non-polar A plane. It's actually the structure we did the microscopy on that I showed you earlier. 2 distributed Bragg reflectors, a quantum dot layer, and a sandwich between the 2 distributed Bragg reflectors. And we then used our microsphere lithography technique to create these little micro pillars. Has to be said, it's a pretty ugly micro pillar, particularly at this stage in the experimentation. We had a lot left to learn about etching, dry etching here, porous GaN. So we've done our sphere lithography, but the porous GaN has really disrupted the dry etch used to form the micropillar and left us with this kind of gallium nitride nanographs all around. Nonetheless, with the 2 DBRs in place and the pillar structure, we really get like very nice bright emission from these devices. We get a lot of counts per second. So we can see here's our nice bright dot. It's at the wavelength, the design wavelength here for the DBR was 435 nanometers. So we're quite close to that for where we're seeing our brightest emission. We've got these nice short lifetimes. In this case, even in the A plane, in the sort of hundreds of picoseconds, sorry, even in the C plane here in the hundreds of picoseconds regime, although not as short as we could do in the best A plane structures. And we can do our Hamby, Brown and Twist experiment. Zooming in here on the dip, we can see that using this cavity structure in this micropillar, our dip is down to 4% rather than some of the ones I showed earlier at 40% of the surrounding peaks. And this we think is the lowest value of that dip that's been reported to date for an InGaN single photon source. It's arising because we have very good light extraction using the distributed Bragg reflectors. That enables us to change the pump regime and really just tickle the dot rather than exciting the kind of surrounding quantum well. So the DBRs are really enabling us to access this much cleaner, more spectrally pure region of emission. Where else might we go in future? Well, almost all the devices I've been talking about so far this evening have been blue emitters. But I said at the beginning, oh, we could do tons of different wavelengths with the nitrides. Actually, those different wavelengths are hard to do, okay? Nitrides are really good at blue, we're kind of good at green, and we're not bad at near UV, but crossing the entire visible spectrum and getting out into the infrared or the ultraviolet is difficult. With one of my other interests, with working with the PoraScan and with my spin-out company Poratech, we've been working for quantum wells on making red micro-LEDs using PoraScan and indium gallium nitride. If you'd asked me 10 years ago, was I going to do red LEDs in GaN, I'd have told you were stupid, you didn't need to, and it was all going to be great because everyone could do that in indium aluminium gallium phosphide. But for micro LEDs, the phosphide materials have some shortcomings, and we're driving towards all nitride micro display technologies. And that's kind of inspiring as to what we might do next with single photon sources. Might we be able to make red or even infrared single photon sources in indium gallium nitride, exploiting porous gallium nitride? That's a question for the future. Okay, thank you very much for listening. I'm totally happy to take any questions.
Thank you very much for a very interesting talk. And now the floor is open for discussions and the questions. If you have any questions, please write on the chat or raise hand.
Yeah, I'm totally happy to answer questions either way.
Now, in terms of the power level, what kind of power are we seeing in those devices?
So I don't know if I can really talk about it in power level. I think we probably talk more in terms of counts per second, so number of photons per second. So if we look at this device, this particular photon quantum dot is saturating at about 4 times 10 to the 4 counts per second, and that would be pretty typical. So kind of tens of thousands of photons per second is what we're managing to get out of these devices so far. We should be able to get higher than that because the emission rates are much higher than that. It's really to do with perfecting the extraction efficiencies.
Okay, thank you very much.
I have a question. What doping do you think you have in the quantum dot? And can you increase it to a very high doping to reduce the electric field within the dot?
Yeah, really good question. So we will have a little bit of oxygen doping within the quantum dot. The other studies we've done on not InGaN in dots, but InGaN in quantum wells or in test structures where we can kind of access the doping more easily, suggests we do have some oxygen doping. When we have done and we have tried intentionally doping the quantum dots, we've found that it basically kills the luminescence. We're not quite sure why. So you don't see good dot luminescence in the highly doped structures at all. So for quantum wells, you can certainly use high doping to shield the fields to a greater or lesser extent. In quantum dots, we have yet to make it work. Something's going on in terms of either it affecting the growth of the quantum dot in the morphological sense, or affecting the states in the quantum dot and preventing the single photon emission that we're looking for.
Let's see, I have a kind of a follow-up question. How do you know that the material composition within the quantum dot is uniform?
I'd kind of assume it isn't, actually.
Oh.
So there is, so in the microscopy we can see there are compositional gradients within the quantum dot. In InGaN in general, okay, because of both the fact that this is a highly piezoelectric material and also because of the strength of the indium nitrogen bond versus the gallium nitrogen bond, which are very, very different, and the electronegativity of both the indium nitrogen and the gallium nitrogen bond, you find that we get very, very strong localization of the whole state, even in quantum wells, on very, very small fluctuations of indium content. So we think that if you have like an indium nitrogen chain, so basically just two indium atoms happening to be next to each other in a quantum well, that will localize the whole. So my overall picture, and this is borne out by some of Stefan Schultz's atomistic simulations, is that actually you've got your quantum dot and somewhere within it there is your high indium content region, which is almost the kind of core of the dot, and that's really where at least the whole is localized, which is a slightly different picture than the continuum models I've been showing so far. But it does mean that the whole thing is actually to some extent quite robust to the compositional fluctuations, because there'll just be some high indium point within the dot, which is the most localized state, and the carriers tend to end up there.
I see, thank you.
I've got one in the Q&A, which says, what paths forward do you see for integrating these quantum dots in photonic circuits? So there's lots of different approaches you could take. I think the A-plane quantum dots are perhaps more difficult to think about how we might do the integration. For the C-plane quantum dots, a lot of the time we think about like, we can grow them on sapphire, as most of the devices I've shown here, but we can also grow them on silicon. And we do quite a lot of work in the LED space on separating the gallium nitride membrane from the substrate, and then using transfer printing techniques, you can kind of pick up a disk, which might be a cavity, and put it adjacent to a waveguide and start to build a photonic circuit. Alternatively, I think there are people I'm just trying to think where, probably in Nicolas Grandjean's group in Switzerland and elsewhere, who are making waveguides, etc., directly on silicon on very thin nitride layers. And then you could grow the quantum dots within that and start to build your photonic circuits. What we haven't got yet is particularly good control of dot placement. We have random arrays, but there are people who are starting to look at patterning the surfaces on which the dots grow to control the dot locations, which is something I'd quite like to have a go at. I just haven't had the funding or the opportunity quite yet. Hopefully that answered the question.
I have another question, and perhaps I am not fully understanding how this is working, so forgive me if that's the case, but it seems to me that the dislocation is a certain type of defects are how you're able to form the perossification of the layers. Is that right?
Absolutely.
And so that allows you to form these DBR mirrors. Mm-hmm. But in general, intuitively, I would think that you'd want your defect density to be low. So does that mean that there's some kind of a trade-off when you're thinking about making these cavity style devices where you need a certain number of defects in order to form the mirror layers, but you maybe ideally want that defect density to be lower for other reasons?
Yeah, a really good question. So in fact, okay, so I guess the thing about the nitrides is, yes, we'd love the defect density to be low, but it's not. Okay. So in a way, you're living with the defects come what may, and if you can find a use for them, you're kind of winning. The other thing I would say, though, is there are a lot of techniques and there's a lot of art and handicrafts that we have developed over the years for reducing the dislocation densities in these materials. But that's not actually a showstopper at all for the dislocation-based etching technique, because we can etch fields that are like tens of microns across. So we can take most of the materials I'm showing here have dislocation densities in the 10 to the 8 to the 10 to the 9 regime. But if we took the dislocation density down to the 10 to the 7 or the 10 to the 6 regime, it would still work. It gets to be a little bit more tricky when we get down to the 10 to the 5. It's still just about workable, but there's hardly any gallium nitride that's like that anyway, sadly. So in terms of if we wanted to make, for example, cavity structures in low defect density material, but still with porosity, I would use E log GAN. Now in epitactyl lateral overgrowth, it's a defect reduction technique. You get stripes of high defect density and stripes of low defect density. We would essentially use the defects to access, go down and then access the low defect density material etching sideways. We'd have porous strips which had low defect density, and then ideally we could then locate the cavities on those porous strips.
Thank you. It's very interesting.
No problem.
In your STEM image, it looked like the image was fading as you moved into the defect. Is that because we're looking into the defect?
Yeah, so I think the thing we have to be a little bit careful of here is that we did have to make the TEM specimen. So some of what's going on here is the impact of making the TEM specimen on how the material ends up in the foil. So you can see, like particularly over here in this region, we've got this region which is all looking very dark. I don't think that's how the material is. We have used an iron milling step to finalize the specimen preparation. I think we've milled away excess material there. We know from other studies that where you have a pre-existing hole or other disturbance in the crystal structure, that can be a section when you're placing your iron milling where you more quickly iron mill because the bonds are disturbed and it's easier to knock atoms off. So I think some of what we're seeing here is to do with how we made the sample lookable at in the TEM, not actually really to do with the original structure. All of which means that I'm not necessarily 100% sure that the diameter of the pipes we see is exactly what it was in the as-grown pristine material as well.
I see, thank you.
Is there any more question from the audience? If not, then I'd like to thank the speaker for the very interesting talk. We learned a lot.